microservice architecture. So of it, there has been a movement towards microservice architectures, which is just a fancy name for, instead of having multiple components of your app run in the same container or a virtual machine or a physical bare metal box, the microservice architecture phenomena suggests that you have one process, one container or one virtual machine per component. For example, if you have a 3-tier app, you'd want your web tier to run in one container, your application engine to run in one container, and your database to run in one container. So it basically enables you to isolate the smallest possible unit of your application, and also it kind of encourages you to recover quickly, which means that if a container or a VM that is running your app server, for example, crashes, you should be able to recover from by spinning up another container for the same tier, so that it remains pretty much stateless. So microservice architecture highly encourages you to build stateless applications. So at this point, what is a state associated with a containerized app running inside a container, right? So what does a state for a containerized microservice architected application mean? The classic example I like to give in this context is that I participated in DockerCon hackathon in June, and there were about 50 teams that built applications in microservice architectures inside containers, inside Docker containers, and every single team had state associated with their application. None of them built a database, but every single team that built an app inside a container had state. So state inside an app would mean secrets like private keys, public keys, etc. So if your app tier crashes on app tier virtual machine or a container crashes on one node, if the scheduler starts it up on a different node, you do not want to lose your private keys and public keys for your TLS communication with northbound APIs or southbound APIs to the database. So secrets are state associated with the container. Let's go to the third point, logs. So if something goes wrong with your application and you're required to collect support bundle, you want to have logs that corresponded to the app running on node 1. You don't want to lose them. So that is one use case for logs. The second use case for logs is you might want to run analytics. You might want to data mine the logs at a later point in time. So that is another use case for why you want to preserve the logs that are written out from your app running on one node after it got scheduled to another node. And of course, if your application tier is a database tier, you want to store your database files on a persistent state on a storage backend, so that the state that was written out from the first node is still accessible on the second node. And please do stop me at any point if I'm going too fast or if there are any questions and stuff like that. So Flocker is a product that manages, that's a distributed volume manager in container space, specifically built for container space. So the way containerizers like Docker or Rocket or any other containerizer that you built on your own in your house based on LXC, it only takes care of the CPU and memory states of a container, which means that you start up an application using Docker, for example, on one node, and the scheduler decides to start it up on a second node after first node crashes. Your CPU and memory state is handled by Docker, but whatever you wrote out to a volume inside the container at say /data is completely lost. So what Flocker does is it kind of fills in this missing space. So wherever it takes care of the container's state written out to volumes for the entire life cycle of the volumes associated with the container. So by entire life cycle, I mean creating a volume, attaching it to a node, mounting it at a mount point, using it and detach, unmount, and destroy. So it manages the entire data volume lifecycle for the data written out to volumes from inside a container. It also enables the container's CPU, memory, and storage to be associated as a single atomic unit. By single atomic unit, what I mean is that if the container's CPU and memory states are active, its volumes are also active or available. And if the container is CPU and memory states are inactive, then the volume is kept around or destroyed based on the user configuration. So the user doesn't have to do anything explicit to associate the application storage along with the CPU and memory states. And Flocker also migrates data volumes across hosts. So if the scheduler restarts the app on a second node, if first node crash, we make sure that Flocker makes sure that the storage parts of the container migrate along with the CPU and memory. And Flocker also works seamlessly using existing orchestrators. So it's not a separate product that you install or anything. So if you're using the popular container orchestrators like Docker Swarm, Mesos Marathon, Kubernetes, or Giant Swarm, or any other popular scheduler, Flocker integrates with the schedulers, so it works seamlessly. And I'll give you a demo of what I mean seamlessly. So let me skip this slide and this one as well. I just want to do a quick architectural overview of how the storage parts react to compute and memory in the container ecosystem with Flocker as an example, and I'll also do a live demo if we have enough time afterwards. So applications are defined, for the sake of this example, let's use Docker as the choice of containerizer and Docker Swarm as the choice of scheduler. So if you replace Docker Compose and Docker Swarm with Mesos Marathon or Kubernetes or Giant Swarm or any other scheduler, the rest of the storage workflow will still work the same. So this is just for the sake of the example. So user would define an app using Docker Compose as the application manifest. So by app manifest, what I mean is that if I have a three-tier app, front-end, app tier, and database, the manifest for what are the volumes associated with each tier and what are the networking parts associated with each tier, the naming of each tier, etc. All of those would be defined in a Docker Compose file, which is just a YAML file with a predefined configuration. And the scheduler, for example, Swarm, would pick up this Docker Compose file, the YAML file, and decides to schedule the different tiers of the application on different nodes. So let's take, for the sake of example, the first, the database tier of the app is scheduled on node 1. So Swarm, which is the scheduler, sends over a command to Docker Engine, which is just a daemon running on the compute node, saying that I'm about to start this container with this manifest on node 1. So the container that's about to be started, let's take, for example, it's the database container. And the user has specified that I want my database container to have one volume for storing all my data files. And as far as the container is concerned, I want this volume to manifest inside the container at /data. Flocker is a plugin that registers with Docker. So Docker allows different components to register plugins. So a plugin is simply a process that's listening on a Unix socket at /run/docker/plugins on the compute node. So as long as you write a process that registers callbacks that can handle creation and attach, mount, detach, those kind of operations associated with a container, and it's exposed via Unix socket and /run/docker/plugins on the compute node, Docker will simply hand you over a callback. So Docker Engine would say that, okay, I'm about to start this container on this node, and there is a volume associated with the container which is defined in the manifest in the Docker Compose file. please do whatever is required to manifest this volume on the compute node. So the plugin is a simple relayer of the message to a central control service. So Flocker exposes a central control service, which is portal to outside world. By outside world, I mean schedulers or end user that's typing commands from the command line on your laptop. So Flocker control service receives this message, and it is aware of the state of all Flocker created volumes across the cluster. So it knows that this is the first time I'm creating this volume. So there doesn't exist, the volume is currently non-existent inside Flocker cluster. So it, So it sends over a message to an agent. So Flocker also has an agent running on each compute node. It sends over a message to the agent saying, hey, please create this volume for this app on this compute node. So what the agent does is, agent is composed of 2 layers. The top layer of the agent simply knows that I need to create this volume on this node, and the container needs the volume to manifest inside the container at /data. So it issues a set of commands to a storage driver, and this storage driver varies based on the kind of storage you have configured in the backend. So for example, if you have EBS, there is a EBS driver that's registered with Flocker agent, or if you have Cinder, you have a Cinder driver, or NetApp, or EMC storage, etc. So each storage driver implements the API calls according to the storage backend of choice. So Flocker node agent issues calls to the backend storage driver saying, create this volume and manifest it inside the compute node for me. So at the end of manifestation on the compute node, if this is your OS, let's say your OS of choice is Ubuntu, at the end of manifestation, you will have the volume associated with the container at /flocker/uuid. And this path is associated, how do we get to this path? So if you create the volume, attach it to the node, the volume will appear at /dev/sdf or a location similar to this. We format it using ext4 and mount it on the compute node at /flocker/uuid. So once this path is available on the compute node, the path is relayed to control service, and a control service relays it to Flocker plugin, and Flocker plugin relays the path to Docker engine. So what Docker engine does at this point is that it simply bind mounts this path into the container at /data, and at that point it says, okay, the container is now up and ready and it's open for business. So when the app inside the container writes out to /data, it's actually on the host, it's being written out to /flocker/uuid. And if you go down the storage path, if EBS is your storage backend of choice, it's actually being written out to /dev/sdf. Is the workflow?
Can you do that with EBS snapshots as well, or just with new and fresh?
EBS snapshots is something that's currently being worked on. Creating a volume from existing snapshots is a very important use case for CI workflows, etc. So that's something currently being worked on, but it doesn't exist in the latest Flocker release. Okay, let's look at a demo which makes things a bit more clearer, I hope. So I have a 2-node cluster similar to this architecture diagram that we just looked at. So I have node 1 and node 2 both running Ubuntu 14.04. So if in a Vagrant VirtualBox environment, so I'll SSH into node 1. So it's running Ubuntu 14.04. If I look for Docker engine is running on this node, And the Flocker Docker plugin is the plugin that is this plugin that we just talked about. And if we look at the Flocker processes, so the control service is running on node 1, which is this process out here. And forget about the container agent, it's something that's used for testing. Flocker dataset agent is the node agent that I just talked about. So dataset agent is comprised of both the top and the bottom half, so it includes the storage driver. And for the purpose of this demo, I configured the environment with ZFS as the storage backend of choice, which means that both node 1 and node 2 have local storage with ZFS on top of it. And there is no shared storage between node 1 and node 2. So let's go ahead and start a small container. So I'm specifying, before that, I want to show you so there is a Flocker plugin registered with Docker Engine. If you want networking solution like vWorks or any other networking solution in container space, you would see a second socket for handling network callbacks when the container is starting and stopping, etc. So I'm going to start a Docker container and specify volume driver to Flocker. I'm going to give the volume a name, so let's call it CodeChicks. And I want the volume to manifest inside the container at /data. And for the workload of the container, I'm running a small busybox image, and I'm going to echo hello to /data/state. So here we are asking Docker Engine. I am not using Swarm for this first level demo. If we have time, we can do another demo with Swarm, but I'm starting the workflow from Docker Engine on node 1. So I want the volume driver as Flocker, and I want the volume with a name, and the volume will manifest inside the busybox container at /data, and we are echoing a simple hello to /data. So let us see if the state we wrote out actually got written out. So we wrote hello and we got hello back. And if I exit node 1 and enter node 2, so this was the simple workflow of starting up a brand new container with a brand new volume. So control service simply asked node agent on node 1 to manifest this brand new volume for us. So the next step would be, what about if I go to node 2 and try to access the same volume associated with the container? So if I specify volume driver to Flocker and access my CodeChicks volume and run a busybox image, so notice the time it's taking for this container to run. So what's happening behind we got the hello back that we wrote from node 1. So what happened behind the scenes is that we went on node 2 and we asked Docker Engine here to start the container on this node, and Flocker plugin got a callback and it asked control service, hey, please manifest the CodeChicks volume on node 2. And control service now knows that CodeChicks volume is actually, because we are using ZFS and local storage, control service knows that CodeChicks volume is actually on node 1. So it orchestrates a workflow between Flocker agent on node 1 and node 2, which internally does a ZFS send and receive. So we are actually shipping the contents of the CodeChicks volume from node 1 to node 2, and it's manifested inside node 2 at /Flocker/UUID. if you happen to use, so this is where your content of Cortex volume is actually residing. If you happen to use a shared storage like EBS or Cinder, you're not physically shipping the contents of the volume. You're just changing the plumbing so that the volume is unmounted and detached from node 1 and attached and mounted on node 2. So you can expect a tangible amount of, you can quantify the amount of time it takes to migrate the volume, which will have an upper bound. I think at this point I'd like to take questions. We have 5 more minutes. Yeah.
So for the you have 5 more minutes for your talk.
Oh, okay, sorry.
Yeah, we have 5 minutes for your question.
Oh, okay, cool. Yeah.
So you mentioned that if you have shared storage, then sort of detached from node 1 and attached to node 2. So what if you have both the containers running and you want access to it on both ends at the same time?
If you want access to simultaneous access from both nodes, it wouldn't work for several reasons. The reason being, the volumes are currently, if you use Docker as a containerizer, the volume is identified using a name, and mapping the same name from 2 nodes is not like completely tested or a supported configuration. So the one person that has tried it in the past, he ran into like containers hanging, so it's not a supported feature as of now.
The other, so I have another question.
Sure.
So when you mentioned about ZFS,
Yeah.
and the fact that you were doing ZFS export and import, so is it required in that case to have the same storage in both ends? What if you have ZFS on one node and something different on the other node? How does that work?
So cross storage type movement currently doesn't work. So the way Flock is configured is that when you install the package for each node agent, it needs to be installed with the storage backend choice, and it only identifies, it's only aware of the volumes that are in the same storage backend type. So for example, if I go on node 1 Flocker agent, if I say list all Flocker volumes, if node 1 is configured with ZFS and node 2 is configured with EBS, they will both see disjoint set of volumes. So the identification of I'm a volume and I belong to this Flocker cluster is unique to the storage backend of choice.
And it's the Flocker agent that's configured with this type?
Yes, yeah.
So you can't have an agent supporting multiple types?
Well, it's in the works, but it's not, currently it's not supported.
I'm understand to this. Do you guys have a use case for having a shared file system like Lustre or Lustre or something like that?
Yes, so most of the use cases so far, people, the POCs and all the other work that's happening so far is people are favoring block device backends a huge amount when compared to peer-to-peer. So the only non-ZFS peer-to-peer backend that is currently being developed is ObjectiveFS, which is a file system with object packing. But other than that, there hasn't been a huge demand from DevOps and sysadmins for the file system backends. Yeah, because usually like for the high performance workloads like databases and stuff, you don't want to go through the entire file system layer. Yeah. Have a question?
So how large is the scale that this Flocker system can support?
So there isn't an upper limit on the number of volumes yet, but the deployments for Swisscom, I believe, was a couple of at least 100 nodes, and I need to double check on that. But there is a POC in process for Salesforce, which uses seven compute nodes. So the scale of it hasn't been completely tested out yet. But as far as the code is concerned, there is no upper limit, because each node agent only takes care of the volumes that are visible to itself. So there isn't a shipment of huge amount of data across across the nodes.
You have a central component.
Yes, so this guy, control service talks to each node agent, and what is being shipped is the local state that is visible to the current node. So each node talks to the control service, and the nodes don't communicate with each other. Each node talks to control service, and control service talks to the node agent. There would be scale limitations possibly on the control service, because as the number of node agents grow, that hasn't been benchmarked or tested out yet. So far there hasn't been recorded people trying to use it at such a large scale that it needed to be benchmarked.
Are the access controls, would you need to set up a different Flocker control service
Yes.
for a different environment?
Yes.
It's wide open, so you can just say, I want this container, and it'll give it to you without any sort of access control.
So all the communication between node agent and control service is TLS protected. Control service and outside world is TLS protected. So as long as you have the certificate set up, you should be fine. Does that answer your question?
Yeah, I was just kind of wondering if there was any sort of more granular level of access control within that whole ecosystem there.
Oh, so are you referring to user-defined access controls, as these set of users need to have access to these set of volumes only, that kind of stuff?
Yeah.
No, there isn't yet, but it is on the roadmap, hopefully in the near future.
And you may have mentioned this, but I think I've understood it. If there was shared storage, then you brought the other node up, would it just tell it what would happen if it was shared storage?
If there is shared storage, are you talking about adding a new node or access to the volumes from the existing nodes?
So in your example where you brought up node 1 and you
Yes.
brought up the first instance, and then you switched to the second one and
Right.
you had to move it over,
Right.
then would it just simply tell the new one, oh, it's over here?
Yes, yeah. So the workflow for shared storage would, what would happen is that, so let's say we have EBS. When we started this is the OS. When we started the container on this node, what would have happened is that it would have created this brand new volume, attach it to this node. At this point, you will have /dev/sdf, and you format it using ext4, mount it at /flocker /uuid, and bind mount it into the container at /data. So when we shut down the container here and start it up here, control service will orchestrate unmount of this location and a detach and an attach here. After you attach here, it might manifest on the OS at a different location based on what's available on this host, SVJ, and mount it on the host at /flocker /uuid, and present it to Docker engine, which will bind mount it inside the container at /data. So it's like changing the plumbing from this node to that node. Yeah.
Does the control service also take control of the scaling? Let's say text user traffic and automatically.
Not yet. It's very the product 1.0 was released in June, so it's very, very young. Any other questions?
How is the control service be developed? Is there a single instance?
Yes, so currently it's just a single instance, and users have chosen to deploy co-located with one of the node agents, like the example I just showed you, but most users prefer to have it on a separate compute node. HA protecting the control service is something that we are talking about. It's not, so control service state is written out to a file on local file system. So it's very rudimentary HA right now. It's manual failover. You just have to copy over the contents of the file to another location. But more automated HA of control service is something that's being worked on.
So the time is up, and we give her a big applause. If you have a purchase token
thank
for
you.
you, Madhuri.
Thank you. So if you'd like to, just 1 minute, if you'd like to try out what I just showed you, the tutorial, you can go on GitHub at Volume Plugins Demo. You would just need Vagrant and VirtualBox set up for trying it out. The example that we just ran through, it should take about 20 minutes of your time to play through. I'll be around rest of today, so if you want to try it out and come back with questions, happy to.